Hi everyone. In this video, we want to start learning a bit more of the details of polynomial functions. So we're going to start with this sort of messy looking definition of a polynomial function, with the plan being we use that to help us determine whether or not an equation is a polynomial. And then the next step will be to start with the equation and let that determine what the graph looks like. So we want to be able to look at that equation and have a pretty good picture in our head of what that graph looks like. And we're going to take a little bit different approach to graphing this time. It won't be transformations. So that's why this one gets separated out a little bit along with rational. We'll use some other information to help us get a decent rough sketch of these. Okay, so first thing, we have this equation, and it might look a little bit scary with all the indexing, but we're basically saying that a polynomial function looks like a number times x to some power, and then you can have a different number times x to the next smallest power, and next smallest power, and next smallest power, until you get to just a constant. So we've seen this before. We've looked at quadratic functions, and we've looked at cubic functions, and we've looked at linear functions. These are all polynomials. And a really important thing about polynomials and deciding what their graphs are going to look like is the degree. So linear function is a first degree polynomial because the highest power you see on your variable is 1. A quadratic is a second degree polynomial because the highest power you'll see on your variable is 2, and a cubic is a third degree polynomial because the highest power you'll see on your variable is 3. So it doesn't matter what order we write the terms of a polynomial in, it's all about the biggest power that you see. That said, the way this definition is written, where the biggest power comes first and then the next smallest power and so on, this is called descending order. You don't necessarily have to remember that, but we'll use it a lot. It's kind of nice to organize things so that we can see what's going on. So not mandatory, but we do often use that. And in that case, we always put the biggest power first, and you really can use that first term to decide the degree of your polynomial. Another little bit of vocab that is maybe worth remembering is leading coefficient, and you maybe heard that when we talked about quadratics. If you've written your polynomial in descending order, the leading coefficient is always going to be that very first coefficient that you see. If it's not in descending order, the more general way to think about that is it's always the coefficient attached to the biggest power of your variable that you see. So you might wonder why all of a sudden we have all this subscripting a sub n minus 1, a sub 1, a sub 0. Really, this is tied back in. It's the same idea as when we said the general form of a quadratic is an ax squared plus bx plus c. We're just trying to give ourselves a little more freedom. So if we were going to rewrite a quadratic in this form, it would be an a2x squared plus an a1x plus an a naught. That would be the general form. And this is just freeing us from the alphabet, which kind of restricts the number of terms we had. Technically, we could have a 30th degree polynomial, and there wouldn't be enough letters in the alphabet to make that work. So when we want to allow this pattern to just keep going and not put any restriction on the number of terms, we go with this subscripting. So we pick a single variable a. Notice that a always has to be a real number, so we're not putting variables in there. That's just a constant out in front. It can be a fraction or a decimal, but it's a real number for sure. Another thing to notice is that just like with quadratics, you don't have to have all of those terms for it to be a polynomial. So your a1 or your a2 or your a sub n minus 1, any of those could be 0. The only one that cannot be 0 is the a sub n, because the degree wouldn't be n if that term got wiped out by a coefficient of 0. So that's the only rule. Whatever that highest power is, that determines our degree. So when we're kind of trying to formalize this, we say that coefficient can't be 0. Other than that, the only rule I think we maybe haven't touched on is that n does have to be a positive integer. So the quadratics, the cubics that we reference, those are all great. We can't have a negative power. As soon as there's a negative power, it's not a polynomial. Not that you can't have a function that has a negative power, it's just that it wouldn't be a polynomial. You can't have fractional powers, you can't have decimal powers, you can't have radicals in your powers. They have to be positive integer exponents. Every single power that shows up on a variable has to be a positive integer. You could potentially have a weird exponent on one of your coefficients, but again, if it's attached to a variable, it's a positive integer. Also on this page, we have this list of properties of graphs of polynomials. I'm not going to run through all of these right now because they'll come up as we're working through some examples, but use this list as a reference. So come back to this after you've done some practice and work through some of the examples and try it now, or maybe even the mixed practice, and just look through the list and see if you understand what all of these things are saying. They can look kind of crazy and notation heavy, but it's just kind of your short list of these are the things that help me graph polynomials. Okay, so the last thing I do want to do before we get started is to remind you that we do know about the basic shapes of some of the simplest polynomials. That's the power functions. So I'm going to start at x equals 2, but actually, I'm sorry, not x equals 2, p equals 2. If p equals 0, then what we're getting is y is a constant. So we actually do know that. And if p equals 1, then we're getting y equals x. But I want to see the pattern for powers bigger than 1. So if the power is 2, we get x squared, which is our classic basic parabola. That's a y equals x squared. If the power goes up to 3, I'm going to move that up a little. We get this basic cubic shape, y equals x cubed. If the power goes up to 4, it's going to look a lot like y equals x squared, but it's a little bit more flattened out at the bottom, a little bit more squared off, and then it gets steeper in a hurry than y equals x squared. So I'm not going to do a great job when I reproduce that by hand, but you could check those out in technology if you want to see the little changes in the shape as those powers get bigger. And then if we go to y equals x to the 5th, we get something very similar to x cubed. It flattens out a little near the origin, and then it gets really steep in a hurry. But it is similar to that y equals x cubed shape. And if we continue from there, what we'll see is a pattern with even and odd powers. All of the even powers have this same basic shape. Again, just some changes as we go, with the bottom getting flatter and flatter and the ends getting steeper and steeper. And if we have an odd power, we'll just keep repeating these x cubed, x to the 5th shapes, where it keeps getting a little flatter in the middle, steeper on the ends, but always has that basic shape with the inflection point in the middle. So keep those in mind. We'll use that to kind of help us determine some things about the shape of polynomials. All right, I think that's plenty for intro, so we'll jump into some examples next.